Hello, good morning, everyone. Yesterday, we already explored the concept of one-click hacking as well as iPhone jailbreaking. In terms of one-click hacking, we know that if you click just a single click on a malicious link, or you just scan a malicious QR code, could lead to a full device compromise. But you may argue that I'm a cautious person. I never scan suspicious QR code or click the link from unknown source. Yeah, that's true. But actually, in the real world, there's an even more scary scenario. It's called zero-click hacking. In terms of zero-click hacking, the attacker can launch the attack based on very limited information without any user interaction. For example, based on your phone number, your iMessage account, or your WhatsApp ID. So that sounds very crazy, but that happened many times in the real world. In the next talk, we will move a step forward, and Boris from Kaspersky will share us the real-world example of zero-click attack and against iPhone. Let's welcome Boris.
Hello, everyone. It's such big pleasure to be here at GEEKCON and present for such nice audience. My name is Boris Larin. I'm a security researcher from Kaspersky. And today I'm going to tell you the story that happened with us last year. It's a story that we call Operation Triangulation. So what is Operation Triangulation? It's a targeted attack against Apple iOS devices, against iPhones, iPads, iPods, and it's used a previously unknown and highly sophisticated malware. For infection, it's used a zero-click attack chain, so infection was happening without any interaction with the user, and this attack chain, it used zero-day vulnerabilities. And it was discovered by Kaspersky at Kaspersky. So how we found it? So inside of our offices, we have a special Wi-Fi network. It's dedicated to mobile devices of our employees. And this network, it exists so every employee can go to internet with a personal mobile device, but this network it's isolated from all of our internal systems, from our servers. But still, everything that happens inside of this network, all network activity gets logged, and then it's checked for suspicious stuff. So once we found something really suspicious, there were periodic connections made from several iPhones of multiple employees. And these domains that we used to make connections, they looked really suspicious. They were not known to our Kaspersky security network systems. They were registered with Namecheap and protected with Cloudflare. We also have seen a large amount of outbound traffic happening to these connections from these iPhone devices. And there also always were some iMessage activity right before these connections were made. So for us, it was a signal that it's time to do forensic analysis for these iPhones. And we really found some traces of exploitation when we made backups of these phones using iTunes. And so what we found was traces of deleted iMessage attachments. And there also were some network activity from some processes that normally should never do any network activity. And for us, it was all just the beginning of our research. It took months, but step by step, we were able to acquire, capture, and analyze all the stages of this cyber weapon that was used against us. And today, I'm going to tell you all the technical details about it. So, the exploitation happens with a malicious attachment that is sent via iMessage and executed without any interaction with the user. So all happens in the background when phone lays on the table and the user doesn't do anything with it. And this attachment, it's a PDF file, but the exploit was inside of this PDF file. It was a true type font. And I'm sure that most of you, you met true type fonts in your life if you used computers, because it's the most common file format for fonts in the world. It was developed by Apple in '91, and these fonts, they include programs written in special virtual machine language. And Apple shared the code in these old days with Microsoft, and it was included into Windows 3.1. And actually, because of this, there were a lot of vulnerabilities found in Microsoft Windows. So to analyze this exploit, I had to analyze this code that was written in this virtual machine language. And so I read the documentation. I started to develop my own IDA Pro plugin so I can disassemble it and read the assembly with quite comfort. But I quite soon realized that this documentation is missing some important details that I needed to write this tool. And so I decided to check the actual code, the actual implementation, to understand how it's done. And I found the handler, I found the table with all the handlers for all the instructions. And instantly I found something really suspicious, something really strange. There were handler for some undocumented instruction that was not mentioned anywhere, not in the documentation from Microsoft, not in the documentation from Apple. Actually, there were no single mentioning of it anywhere on the internet. And it was called FNT adjust. So yeah, as I said, I tried to find any information about it. Couldn't find any, except ancient source code of Windows. And it's the only mentioning of this instruction. So this is the only mentioning. You see that it says that this is Apple only instruction, and it's not supported by the Microsoft. And this is all. And this code, it also goes back to the early 90s. So we have one undocumented Apple only instruction. I think you can guess where the remote code execution vulnerability is. So here's my pseudocode for this instruction. It has some adjustments for points. First it does some adjustments going from the start to end, then does the same going from the end to start. So some adjustments in both directions. And it's really easy to suggest that the developer just copy-pasted this code when it wrote it once, and then also made some small adjustments, because code in these two blocks, it's only one thing that differs between them. But by doing so, the developer made a mistake, because here, endpoint actually, it's the size of this buffer with points. So it should be actually endpoint -1. And because of this, it actually gives the attacker ability to write data in the next buffer that is located next to this buffer with points. And unfortunately, this next buffer contains offsets to other buffers. And this gives attackers ability to quite easily achieve read and write in the process of PDF reader. And this code, from the early 90s, and it's exploited the most common vulnerabilities of the web browsers of the 90s. So I'm not going to go too much into detail for this. But what I want to talk about is a timeline for the fix of this vulnerability. So this instruction handler, all this code with vulnerability, it was there since the early 90s. And then it was silently removed without any CVE, without everything. It was removed in January of 2023. It was removed from iOS 16 and macOS 13. But we know for sure that by that time, attackers have already been exploiting this vulnerability. And actually, I don't know what happened, but I can suggest that maybe at some point, Apple started to receive a large amount of crash logs coming from them. And then they realized that like actually exploitation in the wild is happening, and they decided to fix this. And it's good that they fixed this, but it's bad they didn't notify anyone if they expected or knew about in the wild exploitation. This is simply not responsible. And they fixed it in the new iOS versions, but older iOS versions that were still like an active support by Apple, like they were releasing patches, security patches for them. Like like this vulnerability was not timely fixed, and it was like this instruction handler was removed only after our notification. And to exploit the newer phones, which are based on ARM64E architecture, attackers need to bypass hardware mitigation that is called point certification code. So basically, on newer phones, all the pointers have a simple cryptographic signature in the upper bits of the pointer. It gets signed and checked by special instructions. And if this signature doesn't match for pointer, then will exception happen in the kernel, and the phone, it will simply reboot itself. And attackers use these mistakes of the implementation for this technology. So first, there were too much different pointers signed by pack-either instruction, which basically signs pointers like in default mode with a modifier value equal to 0. And these signed pointers, they could be easily found in memory. So this is how attackers bypass this hardware mitigation. First, they find a signed pointer for the LSIM function, which can give a signed pointer for any function you want by providing the name of the function that you need. And they use it to get the signed pointer for mProtect function. Then they use this function to build a fake macho header file for executable. And they make this fake macho header file to have one export that points to not exported function signed pointer of another module, the LD. And this function, it's not exported for the reason because it could be used to sign any pointer with any k in modifier. And attackers, then after that, after they build this fake macho header and injected it into the list of loaded objects, they can again use the LSIM function to get the signed pointer for this signed pointer function, and then basically fully bypass this hardware mitigation. So after that, attackers execute rob job chain, and they use it to execute an S expression. So here's I show you example for the first stage of this NS expressions. So they use multiple NS expressions. This is the first one, which unpacks the next NS expression. So basically, in Objective-C, it supports special language that looks like this. It's basically just text. It's quite similar to SQL. It's also a query language, but it's quite well, like you can implement any logic you want actually in this language. You can execute like any function you want. It's possible to implement conditions. It's possible to even implement loops. So like actually you can convert any Objective-Type-C code into this language. You just will have to write a very long query that would look like this. I believe that it also could be automated. So yeah, as I said, they execute multiple such expressions. And they use the last one to execute a kernel exploit that is written in JavaScript. So in iOS, macOS, regular apps can execute JavaScript, but without just-in-time compilation. And attackers make the most out of it. So they patch the JavaScript environment by directly patching the memory of the JavaScript core library. And they make the interpreter to have a very large amount of free memory to work with. They disable garbage collection. And finally, they enable special debugging functionality that is called $VM. So with this $VM that actually intended to be used only by the developers of the JavaScript core library, it allows to execute special debugging functions from the inside of JavaScript core interpreter. And these functions can be used to get the addresses of different objects and also get read and write primitive from the inside of script. And actually, like I work in Kaspersky for almost 10 years. I analyze, find new exploits on a daily basis. I found more than 20 zero days in Microsoft Windows and Google Chrome that all of them were used in real attacks with real malware. And this exploit, it was the most sophisticated and complex exploit that I've ever seen. It was obfuscated with Uglify.js, basically just to minimize its size and to make it unreadable. But still, after just simple reformatting, it had 11,000 lines of code. A lot of this code were dedicated to ability to execute native API functions directly from the JavaScript. And actually, this technique is quite popular among PlayStation exploits because the just-in-time compilation also is not possible. And to get this capability, attackers modify JS callback object. They make it to execute a very long chain of gadgets via operator instance of. And this very huge chain of rob gadgets allows them to execute basically any functions they want with any number of arguments and even return the return value to the JavaScript interpreter. And now I will tell you about the kernel vulnerability. And actually, it's a crazy one because it's not common when you see such powerful and easy to exploit vulnerability that exists in memory mapping syscall, which is like the core functionality of the operating system, and allows you to map physical memory to user space, read and write to it. And all this happened because of quite simple integer overflow. So in XNUO operating system, there is a match make memory entry syscall, and it could be used to create memory entry. It takes a lot of parameters. The most interesting ones are the size and offset. And this syscall, it had this check for offset and size. I guess you see where the problem is. It could be trivially bypassed, and it creates a VM entry with a size that covers like the whole memory that's available on the device. And then when this VM memory entry is created, then it will be mapped to some area in user space memory. And VM map that is used to do that, it had this check for the size of the that is written in the entry. And of course, it will be always bypassed for the entry with such huge size. Because of this, attackers basically get the ability to map the memory outside of any object they want. But if they combine this primitive with some special memory object that is mapped into physical memory, it allows attackers to map physical memory to user level. So here's a physical memory map for iPhone devices. And so we have some memory region with hardware registers. We have DRAM, we have video RAM, we have PRAM, which is a volatile storage, a flash. And in VRAM, there is a special object that is called purple graphics mem. This is frame buffer. And it can be used with this vulnerability. So attackers create a malicious VM entry for this object. Then they get the base of this object in physical memory. This is done with special heuristics. And then attackers can translate and map any physical address they want. And they find iBoot handoff. It's a special thing that is left after iBoot is loaded. iBoot is a bootloader for the phone. And this thing, iBoot handoff, it has a map of different physical ranges, and the attackers get a DRAM address from there. Then attackers get the address and size for kernel image. They get it from special hardware registers. And then they find CPU data structures for each CPU in physical memory, and also find a VM page array. And after that, attackers spawn their own thread and find its kernel address via CPU active thread field in CPU data structure. And then attackers convert this kernel address for thread to get its physical address. And then they can get ability to read any kernel address they want via thread get state. So this is full exploitation process to get the kernel read. And you can see that basically all the exploitation is basically just parsing of the memory. And they get the write primitive, like exactly the same way. It's also all about parsing the physical memory. But the method will differ between different devices, but it's still the same idea. So I will not cover it in detail. But what I want to talk about is the way how they bypass hardware mitigations. So in my opinion, the life of iOS attacker is quite miserable. Like, check yourself. To completely hack the phone, you need to have a remote code execution, you need to have a pack bypass, then you need to have a kernel vulnerability, and there, on most of other platforms, like on desktops, on Windows, it will be a complete game over. Attackers can do whatever they want with your machine. But here, on iPhone, on iOS devices, attackers need to fight final bosses. PPL, which is page protection layer, PTRR, which is a protection for the, it protects kernel code from overwrite, and kernel pack. And because of this, even if attackers have like kernel vulnerability plus RCE, they still cannot do anything with your device. They cannot inject a malware into user-level processes. They cannot modify kernel code. Like, they cannot modify some sensitive structures in the kernel. So like, still, after like all this work, they cannot do anything. But turns out that there exists a special feature in Apple chips that allows to completely bypass all these sophisticated, hard-to-hack hardware mitigations. And it makes the life of attackers quite happy again. So it turns out in newer chips of Apple devices, A12 to A16, which like the latest one, there exists a special hardware feature that allows to completely bypass these hard-to-hack hardware mitigations, the kernel memory protection. And for this bypass, it just only required to write the destination address where the data needs to be written, and then also write the data, and write something that looks really similar to the hash of this data that needs to be written to some unknown hardware registers of the chip that are not used by the firmware and actually not used anywhere at all and never mentioned anywhere. So the Apple chip, the system on Crystal, it's not just the processor CPU, but also a lot of peripheral devices all put into a single package. So you can see only some of them on this slide. But actually there are much more. And this CPU works with them via special memory mapped registers. How it looks like. Basically, in your memory, you have some specific address. it's from the site, it looks like a regular address. But if you write some bit there, hardware might do something. And if you, after that, read from some other address, like you might get some data from this peripheral device. And the addresses for all these different peripheral devices on Apple devices, they are all present in a special file format that is called device tree. They are processed by the bootloader. It's binary format. It could be parsed. Here I show example for what you can get if you parse it. And so yeah, like basically it's just a description of all hardware stuff that available on this particular device and where its hardware regions or hardware registers are located. So for example, for this one, you can see that so like the start address for the ACC input hardware device, no idea what it does, but yeah, we can see it's starting address for its hardware and also the size of this region to work with this hardware peripheral device. And exploit use this 6 unknown, never before seen hardware registers. Basically just, they look like addresses in memory, but if you interact with them, something might happen. And I checked different device tree files for different firmwares, for different devices, and found no mentioning for these addresses. After that, I checked different source codes for different XNU builds. I checked, started to reverse engineer different kernel images for different devices. Then I started to reverse engineer kernel extensions, also checked multiple for different devices. I started to reverse engineer iBoot. I even checked the firmwares for different coprocessors and also found no mentioning for these addresses. And then, by experimenting, I found out that Apple M1 and M2 chips for MacBooks also have this hardware functionality. And on MacBooks, you can use special tool. It's called Mini. Basically, it allows to trace all access to any ranges of memory that you want. And I've tried to do that, and also found that MacBooks have this functionality, but it's also not used. So how could it be that attackers know how to exploit these unused hardware registers that are never mentioned anywhere? And also it's quite interesting, but what peripheral device has such capability to bypass these hardware protections? So what I got idea is that it might be worth to check what other known peripheral devices are located close to these addresses. And I found out that actually the memory ranges for GPU's coprocessor are located really close to these addresses. In memory, it all looks like this. So yeah, first we can see that one of addresses used by exploit is located really close to the one region of this GPU's coprocessor, and all others, 5 of them, are located like in the unknown area between 2 known regions of GPU's coprocessor. So this way, it was like the right conclusion was that most likely all these registers are belonging to this GPU's coprocessor. So let's see how they are used by the exploit. So this one is different from all the others. It's located in another region. And it's touched only at initialization and finalization stages of exploitation. And based on my experience, I knew that most likely it either enables or disables this hardware feature, or it's used for controlling the interrupts. And I've decided to move this with this second theory, and quite soon I found out like what this register is used for. I was able to find like exactly same code in source code of XNU, but in the source code XNU, this code, which is used for working with a special core site debugging hardware, it's a special debugging feature that was it was developed by ARM itself, not by the Apple. And in XNU source codes, you can find the code to work with this hardware, but only for the cores of mine CPU. And the code that I've seen in exploit does exactly the same, but because it interacts with a register located on another address, it means that it also works with this core side hardware, debugging hardware, but only for the GPU coprocessor. So it kind of like we solved half of the mystery. But what are the other registers that are located and used by the exploit? So yeah, like this one, we know about it. These two, they used in exploit, like only at the beginning and at the end as well. So most likely they are actually used to enable and disable this feature. Then this one, it's used only on newer Apple chips and just set to 1. And these two, they are the most interesting ones. For these ones, exploit writes something that seemed to me like the flags, and it also writes the lower half of destination address where data needs to be written. And this one is used to write the data that needs to be written along with like hash, and also it writes the upper part of the address, and also that seemed to me like a command. And this is how it all looks like together. You can see that the data needs to be written in aligned blocks of 40 bytes in hex, and all this data needs to be written to the same register sequentially. And after all these steps is done, like this data magically appear in the protected memory. So what can be done with that? So it's possible to patch the page table and inject the malware into user-level processes. It's possible to patch, modify the protected data of the kernel that is stored in PL data segment. And it's even possible to patch the code of the kernel. But like if you patch the code, it will be executed. But after some time, a kernel panic happens. That's what I saw during my experiments. So I was talking about the hash, something that looked like the hash. And it basically this is it. Like on first sight, it looks like some dummy, very dummy custom algorithm, because basically all what it does, it just stores the data with these values provided in this table. And I've looked, like we are an antivirus company. We have a very large collection of files, and I've tried to find some of these bytes in our collection, and also didn't find any matches. So this table, it's fully custom. So my original idea was that, like, most likely this is hardware that allows to somehow bypass, most likely it's some debugging hardware that allows to directly write to the memory is bypass of the hardware mitigation. But like we not instantly recognize this. We've got some help from the community, but turns out that this hash, it's actually something more similar to the checksum. Or more correctly, it will be to call an error correction code. And even more precisely, it's a Hamming code, but with a unique lookup table. And this finding actually gives us some answer. So because of this, like where this algorithm, like Hamming table, error correction code, where they're used? They're used in with work with cache. So like this behavior that we've seen, combined with this fact, it gives us an idea that this hardware feature, most likely, like 99%, that it's a special debugging feature for the cache of GPU's coprocessor. So at least we partially solved this mystery. We kind of know like what these hardware are that was used by the attackers. But still, it's not clear how the attackers found out about it. It's not ordinary vulnerability. First time I see something like this. So what attackers needed to know to exploit it? First of all, they needed to know that such a powerful cache debugging feature exists. And I never, like, working with other microcontrollers, with the desktop processors, I never heard that something like this could exist. They needed to know that it requires Hamming code to work. They needed to know these unique values in this lookup table. And most importantly, they needed to know the location and purpose of all these hardware registers that are involved in work of this feature. And they needed to know how to interact with them and in what order. And it's also interesting is how Apple fixes this. So in this device tree, they have a special table that describes which memory regions should be protected from the access. And this table looks like this. It first goes the physical address of protected regions and its size, then attributes, and 4 bytes ASCII code attack that kind of, it's not used, but it's just present there to like maybe explain for everyone like what is blocked and why. Like it's easy to understand why they block access to PCI, why memory region, why they block access to the device address resolution table and device address filter, because they also could be used to bypass this exact protection. They block access to the physical memory of system memory management unit. So all of these are easy to understand, and all the entries in this table, they're like this. They have quite meaningful tag that explains like what the area is there and why it's blocked. And this is how this hardware vulnerability was mitigated. And like these two entries, like their description, quite different from all other entries in this table. And at this point, attackers have the full control of the phone. They can do whatever they want with it. And what attackers do? Like they can inject malware into user-level processes. And this is exactly what they do. They spawn 2 new processes. They spawn imagent, and they inject a malware payload that clears the artifact of the attack. And they also spawn the process of Safari. And all what they do is to make it go by the provided link that exists in exploit. And all this also happens in hidden mode. User doesn't see anything, but Safari executes the JavaScript code that was received from the server. It validates that it's the right interesting victim. And if it's the right victim, the victim receives another exploit, Safari one. It was also 0-day. And after exploitation of this Safari exploit comes another kernel exploit, which was completely different from the JavaScript one. It's completely different. It's a binary one, but it exploits the same vulnerabilities. And only after that, they execute an additional malware, which is native binary payload. And it checks a lot of stuff about the phone, like is VPN active or not, the name of the Apple ID account and so on. Like there is about 15 or 20 different fields that gets checked by the attackers. And only if it's the right victims that attackers want to infect, they return the final malware payload. So all these stages, like after the JavaScript kernel exploit, they were completely not necessary. But still, attackers, basically like after initial exploitation, they exploit the device one more time from scratch. So all of this is done just with purpose that, in my opinion, just to complicate the analysis of like this attack, just to make sure that nobody ever sees what comes at the end of this attack. So yeah, validator, if it checks that it's the right victim, it gets executed this malware. And this malware, it's a fully fledged APT platform. It was developed in Objective-C. It receives and executes additional plugins. There are a lot of them. And the code has signs that existed for at least 10 years. And what it collects? It collects almost everything. So it gets geolocation, not only location, but also speed and direction. It has full access to the file system, to all the files and databases. It extracts iOS keys from the keychain. For this, it just waits until the user unlocks his phone. It able to get all the data from the messengers, such as WhatsApp, iMessage, Telegram, and possibly much more, because this ability to get information from the messengers, it comes as additional plugins. And for example, if like WhatsApp, iMessage, Telegram, it's the messengers that are most popular in Russia. Like if attackers come to some other country where some other messengers are more popular, most likely they have additional plugins that will allow them to extract the data from the messengers that are popular in this location. Then attackers have full access to the camera and microphone. They have access to address book, and they even, it seems like they have access to other Apple devices that are located nearby. So they get this permission. Most likely it's implemented as additional module, but it looks like they can even build like something that would look like a social graph. Like there is one iPhone, and then they can see what other people iPhones are located close to this iPhone. And maybe they also can infect those other iPhones. And among like the most cool features of this malware, something that we have seen for the first time, is the way how they access the photos. So you can imagine that like how we use our phones. Like I see many people during my talk make a lot of screenshots, and me personally, like during GEEKCON, like I make one photo every 5 minutes. So like thousands and thousands of photos on our devices. So it's hard to process such large amounts of data. How do they do that? Actually, it's really easy to do because Apple devices have a very powerful machine learning capabilities. So here you can see some photos that I made with my friends on the beach. And so you can see on the left what you see, and on the right, you can see what your device sees. So it recognizes that it's a coconut, there is a water on the background, it's all happening on the beach, there is even a strawberry in your coconut. And it even recognized a small text that is carved on this coconut. So these are conclusions for my talk that I want to mention. So I believe we found this sophisticated attack only because we checked our network logs. Apple devices, they're closed devices that you cannot install a security system on, so it's really hard to detect such attacks. But if you have a network logging in your office, in your home, and it's actually it's much easier to implement than you think. Like you will be able to find the more sophisticated APT attacks like this one. And also, what this example perfectly shows is that even the most advanced hardware protections will be still trivially bypassed by the APT group if there are other hardware features that exist, even if they are not mentioned or documented anywhere. And we also see that quite soon malware will know everything about you thanks to machine learning capabilities of your devices. I guess everyone heard about like recent news about Microsoft technology that is called recall. Like quite soon, all of our Windows desktops will be constantly making screenshots of everything that's happening on your Windows operating system, and this machine learning capability will be analyzing these screenshots. I expect that malware will access all of this data like in exact same fashion that we saw in this attack. So yeah, this is the end for my presentation. I will be really happy to talk with all of you and answer your questions in the audience. But now also comes the time for the demo.
Thank you very much for your excellent presentation. Very impressive. Thank you very much, Boris.
Yeah, thank you.
But I really want to open the floor for any one of you have some questions. Using this opportunity, he flew all the way to come to join us at GEEKCON. So I see somebody raising a hand.
Okay, thank you, Boris. It's excellent and brilliant topic. And my question is, what if you are some wonder, just like Google or Apple, with the power of cloud servers, can you build a system to detect such attacks?
Yeah, in my opinion, like the platform holders, like Apple,
Yes.
they have capabilities to detect such attack. And I believe actually like the first part of this attack was actually detected by the Apple, because each time crash happens on your system, the special crash log generated and it's sent to the servers of Apple in case of iOS devices, or to Microsoft in case of Windows system. Like every time something crashes, notification about it will be sent. And it's exactly the same also with the web browsers. Like each time the Google Chrome crashes, Google will receive a notification. And all these crash logs, they could be used to detect the active exploitation and to fix such vulnerabilities.
Okay, I wanted to ask a question about, you said something about ML knowing everything about our lives because of the sheer volumes of data that we put in our phones, including photos and so forth. So I wanted to know, as an end user, what can we do to protect ourselves? Any tips? Nope, we have.
Like, what I learned from this case, what I personally do. Like when I saw all this, I actually stopped to store all my photos on the device. Like each time, like maybe 1 month passes, I've got some amount of the photos. I take them on device without machine learning capabilities. I mean, like after I saw all of this, I learned that it's better to not keep all the photos on your iPhone. Like if, what I do personally is that I make photos like maybe for 1 month, and then I just copy all these photos to my Windows machine without machine learning, and then I remove these photos from my phone.
Thank you. Wonderful advice. I have thousands of photos. Okay. One question, no more.
Okay, so you have all the exploit ready, like iMessage one, the PAC bypass for the user land, and the kernel one, and the hardware bug. You bypass everything, but why do you think they still use the Safari exploit after the kernel exploit? That's my question.
That's also a very interesting question, and it's the one that I cannot give an definitive answer, but I can share you my theory about it. I think that the main infection vector for these attackers is the use of one-click attack chain. It's like the main vector. It's the way how they usually infect the targets using one-click attack chain via a browser. But then they needed this zero-click attack chain, and they developed it. But maybe it was just easier for them just to get the existing code for doing one-click and the new one that they wrote it, and just put it together so they don't need to spend maybe a little bit more time to replicating some other parts of the code that was already written for the one-click attack chain. So this time, most likely these developers, like most of the all developers, are quite lazy, and I believe that they had a lot of Safari 0 days, so they didn't really care. It was easy for them just to save time, just to put two chains together. That's my opinion.
Thank you so much.
Thank you. Thank you.
Okay, I understand you have a demo.
Yeah, so the demo. So organizers invited me here to speak about operation regulation, and when they reached out to me, they told me, Boris, you know, the topics that you're going to cover, it will be hard for you to do demo, but please be creative. And actually, they were right. It was hard to come up with a cool idea for the demo because, all the work that I shared with you, I could have done a demo for how I analyzed this, but I believe it will be either a very long demo or a very boring one because, 99% of work that I did, it was just me looking into IDA Pro in a static way, just reverse engineering all the code. So yeah, it will be a very boring demo. Another option will be to bring this zero-click attack chain here, and just for the sake of demonstration. But for this, I will have to take this zero-click attack chain with me. I would have to cross multiple borders with it on my hands. And actually, this is something this is not something that we do. And yeah, it's against our policies. So I've got actually, I think I've got a cool idea, and I want to use this demo time. Well, I will still show you some demo. It will be a quick one. But I want to primarily use this time as opportunity to talk about topics that is slightly different from the main topic of my talk. And I want to talk about jailbreaking. So maybe some of you heard that some time ago, Apple announced that they prepared these Apple research devices that they give to iOS researchers so that they can do security research, analyze exploits, vulnerabilities without need of jailbreak. And we reached out to Apple after we reported these vulnerabilities to them. We asked Apple to send this research device to us so we can analyze this attack chain, and Apple said no. I believe they just didn't want us to analyze this attack chain and talk about it. So in the end, I believe all these research devices is just a pure PR for them. And but I still was able to analyze all of this, and I was able to do this with the help of jailbreaks, because jailbreaks exists, and if you have jailbreaks, you don't need any proprietary Apple research devices that they will not ever send to you. So yeah, I want to say that it's really cool that there exists enthusiasts who develop jailbreak, and I also think that it's really cool that the vulnerabilities that I've talked about today, the vulnerabilities of operation triangulation that were used to attack us, are now actually used for something good. There exists a new jailbreak that uses these vulnerabilities, and it was actually developed by OPA 334, the Lars, who presented yesterday. And so yeah, I think it's really cool that there exists a jailbreak that is based for this based on vulnerabilities that were used to attack us, and now it could be used for something good. It could be used to enable the security research. If you want to do this security research of iOS, the dopamine jailbreak, the latest version, it's the best thing that you can get if you do not have access to 0 days. So yeah, let me show you the jailbreak that was, I did not participate in development of it, but it's still based on operation triangulation exploit, so I think I can promote it on stage right now. So yeah, it looks like all goes according to the plan. It reboots. So if you want to do any security research on iPhones, you don't have 0 days, or you just want to use cool tweaks, use Dopamine. It's a really cool jailbreak developed by a really cool team of people. So yeah. Thank you, everyone.